Welcome to this comprehensive lecture on sampling distributions. Today, we are going to explore a fascinating and highly practical topic known as the Liapunov Theorem. This is a powerful mathematical tool that helps us make sense of messy, real-world data when our standard statistical rules fall short. By the end of this session, you will understand how to predict outcomes even when your data sources are completely mismatched. To begin, let us think about the standard central limit theorem we already know. It works beautifully when we add up identical random events, like rolling the same die over and over. But what if our events are not identical? Imagine predicting total spending at a festival where visitors include wealthy tourists, local teenagers, and families on a budget. Their spending habits are independent, but they do not share the same financial background. The Liapunov theorem provides a safety net, guaranteeing that their total spending will still form a predictable bell curve, provided no single group dominates the rest. Now that we understand the real-world problem, let us look at how we set this up mathematically. We start with a sequence of independent random variables. Because they are not identically distributed, we cannot assume they share the same underlying population. Each variable represents a unique outcome that depends on chance. To handle this mathematical diversity, we must define the individual properties of each variable separately before we can even attempt to analyze their total sum. Building on that setup, we define the core properties for each specific variable. The formula on screen shows how we calculate the expected value, or mean, for the ith variable, denoted by mu sub I. This is its mathematical center. Next, we calculate its variance, denoted by sigma squared sub I, which measures how much the values fluctuate around that center. Because our variables are mismatched, one might have a tiny variance while another has a huge one. Understanding these individual pieces is the first step toward understanding the whole. With our individual properties defined, we can now look at the total sum, which we call S sub n. This is the main quantity we care about, like the total money spent at the festival. To standardize this sum later, we need its expected value, m sub n, and its total variance, s squared sub n. Because our variables are independent, finding these is straightforward. We simply add up all the individual means to find the center of our final bell curve, and we add up all the individual variances to find the total spread. This brings us to the core of the theorem, the Lyapunov condition. This formula might look intimidating, but conceptually, it is just a mathematical check. We usually set delta to 1, which means we are looking at the third absolute moment. The numerator sums up the extreme deviations or heavy tails of each individual variable. We then divide this by the total standard deviation raised to the power of 2 plus delta. If this entire fraction shrinks to exactly 0 as our sample size grows endlessly large, it guarantees that no single variable is holding the variance. If the condition we just discussed holds true, we get this beautiful mathematical payoff. We create a standardized sum, which we call Z sub n, by taking our total sum, subtracting its expected mean, and dividing by its total standard deviation. The arrow with the D on top tells us that as we collect more and more data, the shape of this standardized sum converges in distribution to a standard normal distribution. In plain English, this means that even though our individual variables are completely mismatched in their shapes and sizes, their total sum will perfectly form a classic symmetrical bell curve centered at 0. Before we apply this to an example, it is worth asking why we use the Liapunov condition. Mathematicians call it a sufficient condition, meaning if it is true, the bell curve result is absolutely guaranteed. There is another rule called the Lindeberg condition, which is actually weaker and more general. If Liapunov is satisfied, Lindeberg is automatically satisfied. However, the Lindeberg condition involves notoriously difficult complex integrals with moving boundaries. We prefer the Liapunov condition in practical statistics and engineering because it only requires calculating standard moments, which is much easier to do. Let us see this in action with a concrete example. Imagine a sequence of independent variables that are growing in size. The ith variable is uniformly distributed between negative I and positive I. Think of this like spinning a balanced wheel that gets larger each time. Because the distribution stretches evenly across 0, the mean for every single variable is exactly 0. Next, we calculate the variance using the standard uniform distribution formula. Plugging in our bounds, we find the variance of the ith variable is I squared divided by 3. Continuing with our example, we now need the total variance of the sum, s squared sub n. We simply add up all the individual variances we just found, from 1 to n. Using the standard mathematical formula for the sum of squares, we know that the sum of I squared grows at a rate proportional to n cubed divided by 3. When we divide that by the 3 from our individual variance formula, we find that the total variance grows approximately as n cubed divided by 9 for very large sample sizes. Now we must check the Liapunov condition. We will choose delta equal to 1, which means we need the third absolute moment. We set up an integral for the absolute value of x cubed multiplied by the probability density, which is 1 over 2i. Solving this gives us I cubed divided by 4, representing the extreme deviations for the ith variable. Next, we sum these third moments for all n variables. Since the sum of cubes grows proportional to n to the 4th over 4, our total sum of third moments grows approximately as n to the 4th divided by 16. We finally have all the pieces to evaluate the Liapunov fraction. We place our sum of third moments, growing at n to the 4th, in the numerator. In the denominator, we take our total variance and raise it to the power of 3 halves, which gives us a term growing at n to the power of 4.5. Because the bottom of the fraction grows much faster than the top, the entire fraction shrinks to exactly 0 as n approaches infinity. The condition is perfectly satisfied, proving our growing variables will still form a beautiful bell curve. It is equally important to see what happens when the theorem does not apply. Let us imagine a highly unbalanced scenario. Suppose our first variable is massive with a normal distribution, a mean of 0, and a huge variance of n to the 4th. All subsequent variables are tiny with a variance of just 1. When we calculate the total variance, the massive variance of the first variable completely swallows the tiny variances of the others. For a large sample size, the total variance is approximately n to the 4th. The first variable is holding almost all the variance. Let us see how this breaks the Liapunov condition. Choosing delta equal to 1 again, we look at the third absolute moment of our massive first variable. It scales with its standard deviation cubed. Since its variance is n to the 4th, its standard deviation is n squared, giving a third moment proportional to n to the 6th. When we plug this into the fraction, both the numerator and the denominator grow at n to the 6th. The limit equals 1, not 0. Physically, this means the first variable is so overwhelmingly large that it dictates the entire shape, preventing a bell curve from forming. This diagram visually contrasts the two examples we just worked through. In the top half, where the Liapunov condition is met, you can see how the individual contributions, despite being different shapes and sizes, blend together smoothly into a perfect standard normal distribution. In the bottom half, where the condition fails, a single dominant massive variable overpowers the tiny ones. It prevents the bell curve from forming, leaving the final distribution highly distorted and skewed. This visualizes exactly why that mathematical limit must equal 0 for the theorem to work. Now that we understand the math, let us look at why this is a cornerstone of applied statistics. In textbook problems, we pretend data is perfectly uniform, but the real world is messy. Imagine an electrical engineer trying to filter out thermal noise in a circuit. The noise comes from dozens of different resistors and capacitors, each operating at different temperatures and generating different interference. They are independent but absolutely not identically distributed. The Liapunov theorem gives the engineer the mathematical justification to assume the total combined noise follows a bell curve, allowing them to confidently design their filters. To wrap up our lecture, let us review the key takeaways. The Liapunov theorem is a powerful extension of the central limit theorem that allows us to work with independent random variables that do not share the same distribution. It relies on the Liapunov condition, which mathematically ensures that the extreme deviations of individual variables are kept in check compared to the total variance. As long as this condition evaluates to 0, no single variable dominates, and we are guaranteed that our messy, mismatched data will reliably form a perfect bell curve. You now have the tools to handle complex real-world statistical problems.